So on the 20th, you guys are going to turn in your assignments for the 9/13 due date and also the 9/20 due date. Okay, so what they did is, since Monday and Tuesday school was canceled due to the hurricane, everything due on the 13th, you guys have until the 20th to turn it in, so you get like an extra week. I would not wait until like the 19th or the 20th to do all of the assignments, because you know that is 2 weeks worth of work, but at least it gives you some wiggle room. I would go ahead and still keep working on them as best you can, and turn them in as you can, rather than waiting till the last minute. And that's for the 18, the 16, and the 14-week students. Now for the 18-week students, on Monday the 18th, so that's this coming Monday, you guys will take your Newton's Laws test, and that's over the things that I'm going to talk about today. On the 14th, the 16-week students are going to take their 2D motion test. Okay, that's tomorrow. And then on the 20th, so that's the day of the test. Okay, so that's important, or I mean the day of the due date. The 16-week kids are going to take their Newton's Laws test, so don't get behind, because usually, like, if a test is due on or you're supposed to take it on a certain date and it's not due until Wednesday, technically it's not late until Wednesday. Well, this one is, you're supposed to take it on Wednesday and it's due on Wednesday. So just be careful with that. Now the 14-week kids, technically the schedule says Monday. You guys were supposed to take your math and physics test. I realized school was closed, so you just need to get it in before the 20th. And then on the 18th, which is this coming Monday, you guys will take your 1D motion test. Okay, and that'll be, again, due by the 20th. So let's go and let's talk about the this the Newton's laws stuff. Okay, so I broke it into laws, and then we'll do some free body diagrams. So Newton's first law is basically the law of inertia. So it's just telling you that inertia is a tendency of an object to remain at rest or to keep moving when it's already moving. So like, I like to tell my students that when their parents tell them to get up for school and they don't want to get up for school and it seems like so hard to get out of bed, that's inertia, right? It's physics that's keeping you in your bed. You want to stay in your bed. You want to remain at rest. That's why, like when you do your Newton's law lab, your Newton's second law lab, and you see the guy, he's pushing the file cabinet at the beginning. It takes him a little while to kind of get the file cabinet moving, but once he gets moving, he starts going faster and faster, right? Because that's inertia. So basically, an object at rest will stay at rest unless, or an object in motion will stay moving unless it's acted on by a force. Okay, so some sort of force has got to cause you to stop, or some sort of force has got to cause you to get moving again. And then we can talk about forces, right? A force is a push or pull exerted on an object, and a force will cause speeding up, slowing down, or a change in direction. So if you remember acceleration, this is basically our definition of acceleration. So a force causes acceleration. Okay, we'll get more into this, like mathematically, in Newton's second law. So now let's talk about a variety of different forces. Now, if you go to the course resource newsletter for this unit, you can actually, let me actually link it for you in the chat box. Not that that'll really help in the recording, but it's on your website. Oh, excuse me, it's under user links. And it's on your those weekly updates I send you guys, it's in there too. There's a little chart that I've made that lists all the different forces, and then you can put, you can fill in the information to kind of keep track of the different forces. So if that's helpful to you, stuff like that, then go ahead, of course, and use that. So the normal force is a straight up and down force, and it's perpendicular to the surface. So I say straight up and down, but I might not have been entirely accurate with that, because it's straight up and down from the surface. So, for example, get a pen color. If you have a surface that's angled like this, then your normal force is going to be perpendicular to that. So it's going to be straight up and down from the surface. So this should be a 90-degree angle. Sorry, there's like a little thing in my tablet that's causing a little break. But anyway, that should be 90 degrees. So that's the normal force. It's perpendicular to your to the surface, and it's equal to the weight of the object. Okay. So your weight is your mass times your gravity, which we'll get to. But your normal force is basically equal to your gravity. So it keeps, or your weight. So it keeps your, for example, in this picture, it keeps the box from like falling through the table, which I know doesn't happen, but it doesn't happen because of the normal force. And it also keeps the box from floating in the air, which again, I know is doesn't happen, but that's because of the normal force and the weight. Then we can have a drag force. This is a force exerted by a fluid on an object moving through the fluid. So it's always opposite motion. So you can see in this picture, the drag force is the opposite of the airplane's movement. So it's behind, it's in the opposite direction of the movement. So the thrust of the airplane is to the left, and the drag is to the right. So it's the opposite. Okay, and these will be important when we start doing our free body diagrams. So friction is always opposite the motion as well. So I like to call drag air and water friction because it opposes your motion, and then friction is like, you know, it's like it's in the air, like when you're, it's normal friction. It's always opposite motion. Static friction means not moving. So if something's not moving, that's due to static friction. And kinetic friction is moving. Okay, so in these examples, we have an air hockey table. The way an air hockey table works is it reduces the friction, and that's what causes the puck to just slide up and down all the time, or slide around. You have here a match. Okay, the friction between the striking surface and the match is what causes the match to light. In this one, it looks like the car is applying the brakes, and it looks like it was probably a race car, was going really fast, and so that's why we have all this smoke here. But the brakes are actually basically increasing friction, trying to get the car to stop. And then here you have an ice skater, and he is trying to like dig into the ice to cause friction so he can stop and slow down, because when you're ice skating, ice typically doesn't have a lot of friction. So then we have a tension force. The tension force is a force exerted by like a string or a rope. And we like to assume that all strings or ropes are massless. They have no mass. We don't worry about the mass of a string or a rope when we're doing something. If something is hanging, the tension is the weight of all the objects hanging from it. So your tension force is going to be equal to your weight force if something's hanging. So now we can talk about Newton's second law. This is the only one that has an equation or math associated with it. It basically says that the force on an object equals the object's mass times acceleration. And force is measured in newtons, so that's the unit you're going to want to use in your labs and your all your work. If you're solving for force, your units will be force, okay, or newtons, sorry. And then your acceleration will depend on your force and your mass, right? Because we could rearrange this equation to get acceleration. So this is one of those equations that'll fit in a triangle. So you can, force is all by itself, so I'll put it up here. And mass and acceleration multiply by each other, so they'll go here. So you can use it. You could see that acceleration is equal to force over mass. So um, they are related to each other. Okay. Now we'll do some math for that in a second. Now Newton's third law says for every action there's an equal and opposite reaction. So I'd like to say when I was a kid, my brother would like kick me or whatever, and it was just, I would tell my mom, you know, I couldn't even help it. My leg just automatically went out and kicked him. It was like a, you know, I just could not help it. When he kicks me, I automatically kick him back. I just, you know, I didn't know it, but I was trying to describe Newton's third law. Okay, so forces always have pairs and they always act in opposite directions. So when we draw a free body diagram, most of the time we're going to have a force pair. And so you'll have one force that's the action, another one that's a reaction. This is a picture of a guy shooting a gun. And so when he shoots the gun, right, the action is the bullet going away from him. And the reaction is that reactive of like he's getting pushed back because of the force of the bullet going away from the gun is causing him who's holding the gun to go backwards, the opposite direction of the bullet. So now we'll do some free body diagrams. So while we're doing them, I'll kind of talk to you about, you know, what do we need to make a really good free body diagram. So with free body diagrams, you just draw a circle. Okay, you don't have to draw the creature or anything like that. You just draw a circle. So some free body diagrams with different people or different animals or whatever is in your, for example, this is for a human that falls from an airplane without a parachute, but you could have a dog that falls freely from an airplane without a parachute. And the free body diagram will look the same because the human or the dog is just this ball. This is the thing that we're drawing the forces acting on that thing. Okay, so in this one, we're ignoring drag and air resistance. Okay, and since it's falling freely, it's just in free fall. And so we're going to have a force going down, and that's going to be Fg, and that's the force that's equal to the weight of the human. Okay. So our free body diagram is just this ball with an arrow going straight down, and that's just the weight of the object falling. In this one, we don't show the action-reaction pair because we're ignoring drag and air resistance in this picture. So that's all you draw. Now let's go to the next one. Now it's similar, right? We're still having a person that's falling downward through the air. So we're still going to have that Fg that's straight down, right, which is equal to the weight. You don't have to put equal to weight. I'm just doing this to kind of remind you. You can just do Fg, but you do need to label it, and that's so I know that you know what the right force is. And then we need to have in this one, because he's reached terminal velocity, we are going to include the drag. And what terminal velocity is that is when you've reached the maximum speed that you can possibly fall. Okay, and so that is when your drag is equal to your weight. Okay, so this is a skydiver that's falling downward through the air at constant velocity. And sometimes what I do, I'm not super great at drawing diagrams where the arrows are the same size. You know, my arrows are sometimes a little off. So I'll do this, FD equals FG. And that's just so whoever's reading my graph or my diagram knows that I wanted my drag and my gravity force to be the same size, even if they're not exactly. Okay, so that's showing whoever's reading it that I know what I'm talking about. Let's see. Let me go to the next one. So the good thing about these is they they're not super time intensive, but they are, you know, they're not, you do kind of need to know what you're doing. And notice the arrows are always pointing away from our object. Okay, so I'm going to try and draw my horizontal surface. It's not exactly horizontal. I'm sorry. Okay, so this is, we've got, since we've got a horizontal surface, the first thing I'm going to draw is my gravity force, my weight. Okay, and I'm going to draw that because, you know, we always have that. And then I'm going to draw my normal force because anytime we're touching a surface, we'll have a normal force. That's the reason I didn't draw it in the ones where they were like flying through the air, because they weren't touching anything, so they didn't have a normal force. Okay, and I'm going to make a note down here that I wanted my normal force to equal my gravity force, even if they don't look like they're exactly the same. Okay, now we've got a cable that's pulling at a constant speed across the horizontal surface. It doesn't say what direction the cable is pulling in, so I'm just going to go to the right just because I feel like it. And you can call this like F cable or F applied. Write F cable, just so you know that you can do that. And since it's pulling at a constant speed, that means that our friction force is going to be the same size. Okay. No, that's not entirely straight. And I'm going to write friction over here. Okay, and see how I have these two equal each other? I'm going to write also that I was hoping that my friction and my applied force would be the same, even if they're not exactly the same size. And so this right here and this right here shows whoever's reading it that I knew that these two should be the same size and these two should be the same size, even if they're not exactly. Because a lot of times I'm not going to take a ruler out and, you know, measure 3 inches here and 3 inches here or whatever. I'll just write this and draw them approximately the same size, and then whoever's reading it knows that I meant for them to be the same. Okay. Okay, so now this one's kind of the same, right? Except our cable is accelerating, or our crate is accelerating, sorry. So I'm going to try and draw my horizontal surface again. Okay. I'm going to draw my gravity force. I'm going to draw my normal force because these don't change. And I'm just labeling them. You don't have to write what they equal. I'm just doing that so you know. I'm going to write that I wanted my normal force and my gravity force to be the same size. Okay. I'm going to draw my applied force. That's my cable force, right? The force of the cable. And then I'm going to draw a friction force, but my friction force is going to be tiny because since the crate is accelerating, that applied force is more than the friction force. Okay, and if I wanted to show this down here, kind of like I did the other one, I could put F friction is smaller than F applied. Okay, so it does matter the size of your forces, and up until now you're probably like, why does it bother whether they're the same size or not? Why she's trying to tell everyone that they're the same? Well, the reason is because at some point that could be the same, and I want everyone to know that I know they're supposed to be the same at this point And I want everyone to know that the horizontal forces are not supposed to be the same. So I'm drawing this part to show that I know the sizes of the forces relative to each other. Okay. So now let's see if there's another one. Okay, so now we've got this is an angled free body diagram. Okay, so we're not in the air, but we're not on a flat surface either. Okay, our ant is on a hill. So we're drawing a free body diagram for an ant that climbs at a steady speed up the side of an ant hill, which is inclined 30 from the vertical. Okay, so if I were going to draw, if this was on a coordinate plane, 30 from the vertical would be here. Okay, because it's 30 from the vertical. That's this one is the vertical. Let me draw an arrow so you can see them. This one's the vertical. Okay, so 30 from there would be right here. And so here's my ant. And I'm going to draw his gravity force. Now, gravity is always straight down. Okay. No matter what. Or weight. We can call this weight too. But it's always, that one's always going to be straight down, regardless, even if you're on a hill. But remember, the normal, right, is always perpendicular to the surface. So our normal force is going to look weird here compared to our gravity force because they're not in line, like they were before. Our normal force is perpendicular to the surface, so they're not in line like they were before. Okay, and then we have our applied force. Our ant is climbing up the anthill. Okay, so this is our applied. Okay, and then our friction force. So now you can see our free body diagram is getting a little messier. And I'm just going to draw like an arrow to this and write friction. Okay, so our F applied is equal our friction force. And then our normal and our weight are equal to each other, but they're not in the same plane, so I'm just going to kind of write it like this. Okay, so this one is kind of a little messier looking, but it's still, it has all the characteristics of a free body diagram. You've got this ball in the middle. You got the ball in the middle, and then you got the arrows, and the arrows are always pointing away. Notice I never had an arrow pointing towards my object because that's not how you draw a free body diagram. When I see that, I look at it and I'm like, what? It just looks weird to me because it's, so off. Now here's some Newton's second law math, okay? So we're going to actually use that formula from Newton's second law, the F equals ma formula. Okay, so our mass is 30. That's going to be our m. So Anuja is holding a pillow. The mass is 30.3. When Sarah decides she wants to try and pull it away from her with a force of 10 newtons. So this is our force. And Anuja pulls with a force of 11 newtons. So what is the acceleration of the pillow? Okay. So let's draw our free body diagram here. I'm going to draw a different color just to kind of break it up. Okay, so we've got There's our pillow. And this will be, Sarah decides she wants it and pulls it away with a force of 10 newtons. So we'll have Sarah over here, and Sarah's force is 10 newtons. And then we'll have Anuja this way, and her force is 11 newtons. And then what is the acceleration of the pillow? So the first thing we need to do is we need to see what's the net direction of the force, right? So we need to do our F net. Since these forces are in exact opposite directions, we can just do 11 minus 10, and we'll get 1 newtons, and it will be in, I'm just going to say in Anuja's direction, and I'm just going to say A. So Anuja, or forces are vectors, so we've got that vector component, and so now I can try and work through this problem. So let me find a different color. Okay, so now if I want to solve this problem, my force is going to be 1 newton. My mass is going to be 0.3 kilograms. And my acceleration is, I don't know, but I do know the units are going to be meters per second squared because that's the units of acceleration regardless. Okay. So the first thing I'm going to do is I'm going to put this formula in the triangle because the last thing I like to do is algebra. So I'm going to do F on the top, M and A next to each other, and I'm going to solve for A. That's what I want. So I'm going to cover that up, and A is going to be F over M. Okay, so I'm going to have 1 newtons over 0.3 kilograms. And I'm going to put that in my calculator. And that's going to be an acceleration of 3.33333333333 meters per second squared. Okay, so there's my acceleration. Okay, so that's all you have to do to solve one of these F equals ma formulas. Now notice, I didn't just put my two forces, I didn't pick Anuja's force or pick Sarah's force or anything like that. I went ahead and I found the net force first, and then I threw it in the equation. Okay, that's important. You're not just going to choose someone's force, willy-nilly, or put both of them in the equation or add them together or whatever. You have to take the difference between the two because they're in opposite directions. Now, that's, I just was thinking about it. If I were to take, let's say, then, I don't know, Joe comes along. Okay, let me make a different color that's not as close. Okay, let's say Joe comes along and starts pulling on Sarah's end. Okay, with 10 newtons of force as well. That's going to be FJ. Okay, then we're going to have, well, I'm not going to do it that way. Then our net force would be 20, right? 10 plus 10. So that'd be 9 newtons. And that would be in Sarah and John's direction. So, if the forces are in the same direction, then you would add them. But if it's like the original problem, you would just have 11 minus 10. Okay. Um, and then that's how you solve those problems. So that was all I really had for you. This unit, luckily, if you're not a math person, has a lot of concepts, but not a ton of math. But then in the next unit, we're in the applications of Newton's laws. We're gonna be back to a lot of math and not as many concepts. So if you're not a math person, this this is a great unit to try and improve your grade because it's mostly concepts. Um, and if you are a math person, don't worry, we'll be back to math next unit.